Only one problem.
Yeah, what is that?
Square of a number.
Check if a number is a perfect square.
Yeah.
Right?
None.
Yeah. Okay. Fine. Okay, and some of you, I think, mail me the solutions to the other puzzle, but
Yeah.
I haven't had a chance to see even the emails. I'm sorry, but okay. But then, yeah, I shared the solution link with someone, so I think they'll post the. Okay.
Okay.
So fine. Today, what do we do? Let's do some. Let's solve some problem today. Okay. Fine. Yeah, let's get slightly. I mean, so far I think we were doing only easy problems. Let's just try to increase the difficulty slightly.
Okay.
Okay, so fine. The question is this. Okay, so you are a shopkeeper and you want to buy weights. So you must have seen the traditional shopkeepers, right? So they have a beam balance with them or a spring balance. So essentially, what you do is you keep weights on one side, and you have, I mean, say you measure sugar or salt on the other side, and then you compare. Okay,
Yeah.
and you, I mean, so the customers pay you according to the weight, basically. If it's 2 kg, it is like blah blah rupees and things like that. So let's not go to the pricing part, but let's just work with only the weights part. Okay. And let's say you're allowed to keep weights only on one side of the balance. On the other side, you have to keep some. You're forced to keep some rice or something the customer has purchased. Okay, but you want to be able to measure weights which are between 1 to 120. Okay, right? So the customer can. So the
Between 1
max
to.
120, 120.
Okay.
Okay. And as in, so the materials in your shop, let's say you have, in the worst case, 120 kg of rice. So that's the idea. So you'll have to measure. Okay. So now, what are the weights that you need to buy so that you can measure anything the customer buys? As in, it can range from 1 kg to 120 kg. And you can assume that it will be integral. As in, so the customer is not going to buy something of 1.5 kg. The customer is either going to buy 1 kg, 2 kg, 3 kg or something. It's only integers. Okay, but what is the minimum number of weights that you need to buy so that you put them on one side of the balance? On the other side, you can measure any weight between 1 and 1. Does that make sense? Is it clear?
Yes. Yes.
Okay, fine. So as usual, if anyone knows the solution, you can just raise your hand and get the mic and let it out. Whatever you prefer.
So can we keep the weights on both the sides of the weighing
No,
machine? Only
no,
one
no,
side.
no. You're allowed to keep only one side. I mean, that's the easier version. Let's
Okay, okay.
solve that first so that we can easily move to.
Can we keep the weights that are like 2 raised to 1? So
Okay.
2
2
raised to
raised to
1,
1. 2 raised to 1 is 2,
square.
right?
Yeah, sorry. 2 raised to 1, 2 raised to 2, 2 raised to 3. So that you can add any of that. Suppose like 1, 2, 4, 8, 16,
Mm-hmm.
32
Okay.
until the power of 2, which is less than 120.
What is that power?
64.
Okay. Fine. So
Yeah.
why should that work?
So using that weights, we can create anything till that range.
Why is that so?
Because if you need 3 kgs, 1 plus 2.
No. I mean, I'm asking the why part. Why should that be true? What are you getting when you represent? So it's
It's
if
like
a
binary representation.
yeah, okay, yeah, that makes sense. So what he's saying is, you can represent any number by binary, right? In binary representation, any decimal number. So now the thing is, when you say it's a decimal representation, you mean you are. I mean, sorry. When you say it's a binary representation, you mean it's a sums of powers of two, right? Because you can either have only a 0 or 1 in the binary representation. A 0 denotes this power of 2 is not present in the sum, and if a one, if it's a 1, it denotes that this power of 2 is actually present in the sum. So, for example, 3 is 2 plus 1. But then, if we take a bigger example, let's say 15 or 14, which is 8 plus 4 plus 2 plus 0. This denotes that 8 is there because there is a 1, and 4 is there is a 1. 2 is there is a 1, and there is a 0. Does that make sense? Why this solution works? If the binary representation is unique, then the solution should always work, right?
Yeah.
Okay. Okay, fine. So this is a good answer for you using only one side of the balance. Okay. But now what I'll do is so let's see what is the answer. No? The answer is 1, 2, 4, 8, 16, 32, 64. So the answer is 7. Okay. But that's too much for the shopkeeper. So let's make things easier for him. And then say that he can use both sides of the balance. Okay. But now the question is this 7 the best you can get? When you use only one side of the balance, you can't do better than 7. Okay. So when you use both sides, can you do better than 7? That's the question. Is 7 the best then? Sorry.
Yeah.
We can have 4
Yes.
now.
Huh?
So instead of right now we have one weight for 1 kg, 2 kg, 4 kg, 8, 16, 32, and 64.
Right. Okay.
So instead of that, if we don't have weights for 1, 2, and 4 kgs,
Uh-huh.
then by loading on both the sides, we are effectively having 1, 2, and 4. No?
But how do you? What will you use instead of 1 to 4? As in, what are you? What are the weights that you are going to measure? So you still need the weights, right? Even if you use both sides of the balance.
Yes, but we can load 8 on one side and 16 on
Uh-huh.
an.
Okay, then you will get only 8, right? So 16 minus 8 you will get. I mean,
Yes,
depending on
yeah.
where you load, obviously. But
Yes. Yeah.
the right
Okay.
way to load would be to put the smaller weight along with the material the customer has got. So then you will get only 16 minus 8, right? It's because you're pushing this guy, whatever weight he's having, you're doing it 8 plus.
Yes. Yes. Okay.
But that need not always work, right?
Yes.
But somebody was already curious about using both sides of the balance, right? Who was that?
Yeah,
Even
I'm
when
here.
we
I'm
were
here. Yeah,
okay.
I'm on it. Almost did it. This.
Okay.
I guess you have to use the power of threes. Not
Okay.
sure, but
Okay.
doing it. I'm on it.
Okay. So let's say you do use the power of threes. What would you get? As in, let's say
That's
we use 1 and 3.
yeah. So if two is there, we'll keep
Mhm.
like if it is less than three means then it is obviously two.
Okay.
And similarly, that's what I'm trying to do now. I'm thinking of the cases.
So yeah, as long as you get everything from 1 to 4, then you're okay, right? Because that's all that you can
Yeah, yeah.
get. The best to hope is from 1 to 3. As in, so with 1 and 3, if you are getting everything from 1 to 4, then you're okay, right? But of course, you have to go to 9 and also see. But
Yeah. Yeah, but one and three we are getting up till that. Four we have got that, but I'm just checking the cases if everything is coming or not.
okay, okay. Anybody is doing faster than him on this approach? In checking the cases or just shouting out with confidence that this is the answer?
So I guess yeah, this is the answer. 13927 DT1. If we use this five, we can get any combination possible.
Okay, so let's
Yes.
do some stress testing. No,
Yeah.
how do you get 14?
1 4, right? So
Yeah.
if we to 27 minus 13. We'll keep 931 on the one side and 27 on the other side.
Okay, so that gives you 14. Okay, so how do you get 5?
Okay. 1 and 3 on the one side and 9 on the other side.
Okay, so how do you get 120?
Yeah. So 120 was just a second. So 81 minus but it's
81 minus?
just no 81 plus
Okay.
Plus 39. But 89, 81, 27, 993.
Okay, I see. Okay. Fine. Yeah, that makes sense, right? And that's the solution to the problem. So as someone was saying previously that you have only you want to ignore 1 to 4 somehow. So the way to do that is actually you can get if you use both sides of the balance. So you have 1 to 4. Instead of that, you can just work with only 1 and 3. So essentially, what you have is 1. For getting 2, you will use 3 minus 1. Then for 3, you will use 3 directly. And for 4, you use 1 and 3. Okay. But this is not all. You still need to argue by induction that this is true even for the next power of 3. So which is 1, 3, and 9. Is someone else also talking? Then
Oh.
nice.
Sorry.
Oh, okay. No, in that case, okay, no problem. So this is the idea. As in, what you do is you just work with powers of 3, and then using by addition and subtraction, you can actually get all these numbers because you're using both sides of the balance. So in some sense, this is more like binary. Binary, you're looking at only sum of powers of 2, right? Here, you're allowed to use the difference as well. And that gives you the leverage. Okay? Makes sense?
Yep.
Okay. So let's do one more related question to this and be done for the day. So the related question is this. So we were talking about the binary representation, right? So where we were saying that each number can be uniquely represented as sums of as a sum of powers of 2. Okay. Now what I'm saying is, so you do know, I think you do understand that like base 2, there is also base 3, base 4, base 5, right? Where the idea is the same, but then the thing is the coefficients could be 0, 1 or 2 for 3. So when you divide a number by 3, you actually have something like, you can have a remainder either of 0 when it's perfectly divisible by 3, or you can have a remainder of 1 or a remainder of 2, right? Does that make sense? So you know how to represent a number in base 3, like base 2?
Yes.
You do know that, right? Okay. So now my question is, do you need this uniform thing? So in any of these base representations, what you do is you actually have a number. You keep on dividing that number. Let's say you want base 2. You keep on dividing that number by 2 till it goes to 0. Then you store all these reminders, which can be either 0 or 1. Right. This is how you convert to the corresponding binary representation. Now what I'm saying is, instead of dividing by 2 in each step, I'll give you a set of numbers. So let's say I'll give you 2, 3, 5, 7. Okay. Now in the first step, you have to divide it by 2, take the remainder, store the remainder. The next step, you have to divide by 3, The next step you have to divide by 5, and the next step you have to divide by 7. This is what you should do. Okay. Will you still get a unique encoding? Will you? So in the base representation, we have this nice property that each number has a corresponding unique representation in the base. Okay. Is it true that when you do this, as in you don't do, so this is not base anything, right? So this is, in some sense, in each step I am dividing by a different number. Does that make sense or no?
Yes.
Could you repeat the question?
Oh, so the question is as follows. What I'm saying is, when you do any base representation, let's say base 10 also, what you're doing is you will divide by the same number. So the way to convert, so let's say we want base x. Okay, any number you want to convert to base x. The way to do that is you will keep on dividing by the number by x, and in each step till it goes to 0, obviously, and in each step you will store the remainders. This is how you convert to binary, right? So let's say you have 10. Okay. First you divide by 2, the remainder is 0. But after division you get 5. Okay. Now 5 once again you divide by 2, the remainder is actually 1. And then you get 2 because 5 by 2 is 2. Because you are worried only about the integral. Now you have 2 you be divided by 2, your remainder is 0. Okay. And you do 2 by 2, you get 1. Okay. Now you do 1 mod 2, which is giving you 1. And then 1 by 2 is giving you 0, then you stop. So your binary representation that you have is the reverse. So you have 1 0 1 0, which is the binary representation of 10. Okay. Right?
Yes.
Now what I'm saying is we'll do this process slightly differently. So in each step I won't divide by 2. I won't take the remainder with 2. Rather I'll give you an array beforehand, which will have say 4 numbers. Let's say 2, 3, 5, 7.
Yes.
Now the first step I will divide 10 by 2 and take the remainder, which is 0. Now I get 5, right? Now I'll divide the number. Now I divide 5 by 3. In the previous thing I would have divided by 2 again. But now I have given you this array with which you are supposed to divide. So I'll do 5 mod 3, okay, which is 2. Now I'll do 5 by 3.
Yes.
And then continue the process. Okay.
Yes.
Now the question is, does this also give you unique representation? Like the binary. I mean, it will be very different from what the binary is, but the question is it also unique? As in, are there no 2 numbers? Once you fix this array that I'm giving you, can 2 numbers have the same representation?
So, like, can we divide one number by the same number twice? And
That is also possible. So let's work with the easier version first, right? So the array that I will give you will have only unique integers, which means you won't divide twice with the same number, right?
so if like one number cannot be like, it's like the each integer can be represented by some product of integers, prime numbers.
But the numbers that I'm giving you are not necessarily prime. So for example, instead of 2, 3, 5, 7, I could also give you 2, 3, 4, 6.
Okay.
But what has that got to do with the prime factorization thing? Because this is sum of products, right? Here what you have is you have a bunch of products and then you just sum them, right? That has not got anything to do with the prime factorization. Because prime factorization is more like you are decomposing the number into just products. It is 2 raised to something, into 3 raised to something, into 5 raised to something, and so on, right?
Okay, we can do it this way also, no?
As
Mhm.
if there is a number of 5-digit number, A B C D
Okay.
has the digits. A B
Okay.
C D has the digits. We can while converting it's in binary. While converting it in decimal, we do it as E into 2 to the power 0, D into 2
Okay.
to the power 1, C into 2 to the power 2. That way we do it, no?
Okay.
So here, in the same way, in our new base we have a number A B C D E. We
Okay.
can write it as E plus 7D plus 35C plus 105B plus 210A.
Fine, but then the question is, why should that be unique? That's my
Because
question. Bro.
in the first ABCDE conversion, we can take 7 common. So it could be written as 7 into some X plus E. And where
But you
E is,
can't take 7 out, right? Because
I can take 7 out, no?
but E is not having 7, right?
So E is left out.
Okay. Oh, E is separate now. Okay. Then
E is left out, and E is a number between 0 to 6. So it can represent every time a unique number. I mean, it can represent all the numbers.
what can represent all the numbers? So
The
E
movements.
can be between. Okay. No, let's work with a smaller set. No, so let's assume that I give only 2 and 3 to you. Okay. Let's say you have a number which is AB. Okay. So essentially, what you would, according to you, what you would have is you'll have 3A plus B, right?
What is the number? AB.
Just AB. The digits are AB, I'm saying.
AB. So
We
it
are
could,
working.
by converting it to decimal, we can write it as A plus 7A plus B.
No. I have changed the set. My set is only 2 and 3. I have only 2.
2 and 3. So we can write it as 3A plus B.
That's what I told you. Okay. So now the question is, why should this be AB? B is between 0 to 2. Okay. A is between 0 and 1. Right?
Yeah.
Why is that unique? I mean,
Okay.
Like 8 can't be represented by using these numbers. If we take like 8, that 4, 3, 1. But 4 we have got by dividing 10 by 6. So 6 has already used 3. So means we can't use the number again repeatedly. So if we can we use the number? Yeah, then 8 can't be repeated.
But the thing is, 8 you won't represent it this way, right? See, these guys can represent numbers only between 0 and 5 because you have 2 into 3 as 6, right?
Okay.
So this is like
up
saying
up to 5.
Yeah, that is unfair, right? Because then in the binary, I'll ask you to represent 4 using only 2 bits. You can't, right?
Yeah, that's what I'm saying. Okay, fine.
So I think it will not be unique.
What is a counterexample?
So like if you give an array, so I multiply all the elements of the array.
Okay.
So then all the multiples of that number I get will have the same representation.
All the multiples of which numbers?
The product of the elements of the array.
But you can only represent numbers from 0 to the product minus 1, right? You can't represent numbers more than that. Where will you even go to the multiples? So that's the example here, right? So if you have 2 and 3, you can represent numbers only from 0 to 5, which is 2 into 3 minus 1. Then you won't have any multiples of 6 with you. Right? If you need a multiple of 6, the next multiple of 6 is 12.
I didn't understand what you said.
So what I'm saying, you were saying that the multiples of the product will have the same representation, right?
Suppose I have like your array is 2, 4, 6.
Okay.
So I'm multiplying 2 into 4 into 6.
No, let's work with the 2, 3 example. No? So you have only 2 and 3 in the array. Okay. As in the sizes are, the numbers are 2 and 3. Yeah. So you multiply 2 and 3, which is 6. Okay.
Yeah.
Now, what are you saying?
If you take a number 12, then
That's what I'm saying. 12 you can't represent at all, right? Because I'm saying you can represent only from 0 to prod minus 1, the product minus 1. And you can represent only numbers from 0 to 5. I'm not saying you can represent all the numbers. That you can't do even in binary, right? That's what I told you. So that's a counterexample, right? So in binary, here what you're essentially asking in the binary setting is represent me 4 using 2 bits, just 2 bits. But with 2 bits, you can represent only till 3. You can't represent 4. Now that makes things clear. Or? Okay. So let's have this as homework. So I can tell you the answer. This representation also gives a unique representation. Okay. But figure out how. Try if you can prove it that this is actually unique. Okay. Any questions before we call it a day? Hello. Hello.
okay, no questions.
No questions? Oh, okay. Happy. Fine. Have a nice day then. Chalo. See you.
Bye.
Bye.
Yeah.